Hey everyone, ready to dive into the world of engineering? Let's get started. Operational amplifiers, or op-amps, are essential building blocks in electronics. These versatile components amplify voltage signals and are used in everything from audio equipment to complex control systems. At their core, op-amps can perform mathematical operations like addition, subtraction, integration, and differentiation, making them invaluable in signal processing and analog computing. For aspiring engineers and hobbyists, understanding op-amps is crucial. They are the foundation for many electronic circuits, enabling you to create anything from simple amplifiers to sophisticated filters and oscillators. By mastering op-amps, you'll gain valuable design and troubleshooting skills, enhancing your problem-solving abilities and creativity. In this video, we'll dive deep into the fascinating world of operational amplifiers. We'll explore their functionality, applications, and why they're a must-know for anyone looking to excel in electronics. So, let's get started and unlock the potential of op-amps together. What is an operational amplifier? An operational amplifier, or op-amp, is a high-gain voltage amplifier with differential inputs and a single output. It has two input terminals. The inverting input, labeled as the non-inverting input, labeled as plus. The output voltage is a function of the difference between the two input voltages, amplified by a large gain factor. An ideal op-amp has several key characteristics: infinite input impedance, zero output impedance, infinite open-loop gain, perfect linearity. These traits allow op-amps to perform various functions without loading down the preceding circuit. Common op-amp models include 1. LM741, known for general-purpose applications. 2. TL081, offers low noise and high-speed performance for specialized tasks. Understanding these components is essential for working effectively with op-amps. How do operational amplifiers work? Op-amps amplify the voltage difference between their inverting and non-inverting terminals. The output is proportional to this difference, multiplied by a gain factor. Gain can be adjusted using feedback mechanisms, which are crucial for controlling circuit behavior. Negative feedback reduces gain, stabilizes the output, and ensures linear operation, preventing distortion. Positive feedback reinforces the input signal and is used in oscillators and comparators. Understanding how gain interacts with feedback and input signals is key to designing effective op-amp circuits. Common op-amp configurations. Op-amps can be configured in several ways to perform different functions. Inverting amplifier. Input is applied to the inverting terminal. The output is 180 degrees out of phase with the input. 1. Gain is adjustable through resistor values. 2. Non-inverting amplifier. Input is applied to the non-inverting terminal. 2. The output is in phase with the input, offering a gain greater than 1. Op-amps are also used in 1. Integrators. Produce an output proportional to the integral of the input signal. 2. Differentiators. Output a signal proportional to the rate of change of the input. These configurations are widely used in audio amplifiers, filters, and control systems, demonstrating the versatility of op-amps. Applications of operational amplifiers, P-amps, are incredibly versatile and used across many applications. 1. Signal conditioning and filtering, essential in audio processing and communication systems. 2. Analog, computing and instrumentation, perform mathematical operations and are found in analog to digital converters and data acquisition systems. 3. Audio equipment, used in preamplifiers and equalizers to enhance sound quality. 4. Sensor interfaces, convert sensor outputs into usable signals for further processing. From medical devices to industrial automation, op-amps are indispensable tools for engineers and hobbyists. Wrapping up today, we explored the fascinating world of operational amplifiers, highlighting their significance in electronics. We covered their principles, including differential inputs and feedback mechanisms, and discussed various configurations like inverting and non-inverting amplifiers. Understanding op-amps is a critical skill for electronics enthusiasts. They form the backbone of countless applications, from signal conditioning to audio equipment. By mastering these concepts, you can boost your skills and creativity in circuit design. That's all for today. Stay tuned to TechBlueprint for more clear and practical engineering content. See you in the next video.